Hello, today I'm going to discuss the paper supporting peripherals in intermittent systems with just-in-time checkpoints. Just to give a brief introduction, intermittent systems operate with sporadic power, causing frequent interruptions and reboots. Maintaining the peripheral state like sensors and accelerators is challenging due to volatile memory loss during power failures. Just-in-time checkpointing struggles with peripherals as checkpointing during operations can cause inconsistencies. Energy harvesting devices power these intermittent systems, relying on capacitors to have harvested energy. They enable batteryless operations for applications where traditional batteries are impractical or unavailable. A background on just-in-time checkpoints. Just-in-time checkpoints or JIT checkpoints are crucial in intermittent computation, saving system states before potential power failures to ensure seamless resumption. They play a vital role in maintaining peripheral operation consistency, preventing data loss, and function integrity. While beneficial for seamless resumption, data consistency, and reducing unrecoverable features, they face challenges. Checkpointing during peripheral operations can also cause inconsistencies, potentially leading to errors or operation non-termination. Additionally, associated overhead may impact performance and energy efficiency. Hence, careful consideration is necessary, especially for peripheral operations, to navigate limitations effectively. This is where SAMOID comes into the place. SAMOID is a novel checkpointing system which addresses the shortcomings identified in conventional JIT systems, offering a solution to support safe and efficient peripheral operations by, by allowing programmers to define atomic operation functions. SAMOID selectively captures checkpoints and maintains memory consistency with undo logging during critical peripheral tasks. When atomic functions require more energy than available, SAMR dynamically scales their workload, dividing the tasks into smaller invocations. A crucial aspect of SAMR is its energy profiler, which estimates the energy consumption of atomic functions for a given device. If an atomic function exceeds the energy budget, SAMR executes a fallback routine or scales down the workload. SAMR's operation is summarized in this figure. In creating the atomic functions, programmers use specific syntax and guidelines provided by the SAMOID infrastructure. These functions ensure safe peripheral accesses and avoid checkpoints. Scaling rules and fallback routines are optional but crucial for such efficient operation. SAMOID's execution of atomic functions involves careful decision making based on factors like knob values and energy consumption estimations. By effectively managing the checkpoints and scaling the workloads, SAMOID ensures both reliability and efficiency in peripheral operations. SAMOID's energy profiler plays a vital role in assessing the feasibility of the atomic functions on a given platform. It measures the energy consumption, helping programmers understand if a function's demand exceeds the device's supply. While the profiler doesn't guarantee correctness due to energy variability, it provides practical insights into peripheral behavior. Most studied peripherals exhibit low energy variance with ample margin between their consumption and device buffer capacity, offering additional assurance of successful execution. Now, one of the crucial components of SAMOID is the baseline just-in-time checkpointing feature. The baseline JIT checkpointing system upon which SAMOID builds assumes a JIT checkpointing system with fully non-volatile memory. This system can measure the remaining energy of the device and interrupt the microcontroller when the buffered energy reaches a lower threshold. When a checkpoint is reached, the system stops executing until the energy buffer is refilled, then resumes execution. This baseline system targets peripheral without internal non-volatile state, allowing them to restart arbitrarily after a power failure. However, it's important to note that the baseline just-in-point checking system has limitations. It does not support concurrency of computation and peripheral accesses. Instead, it focuses on blocking the peripheral operations where the microcontroller waits for the operation to complete. This restriction aligns with many peripherals commonly used in embedded systems and peripherals computation accelerators. The baseline just-in-time checkpointing system serves as the foundation of SAMR's innovation. SAMR enhances this baseline by introducing atomic functions and mechanisms for safe and efficient peripheral accesses, which will be which we will be discussing further. While the baseline system handles checkpointing and energy management, SAMR extends its capabilities to support dynamic workload scaling, energy profiling, and fallback mechanisms, ensuring reliable execution of peripheral operations in intermittent systems. So now let's look at the atomic functions which are incorporated in SAMR. SAMR atomic functions are a cornerstone of SAMR's approach to safe and efficient peripheral access in intermittent systems. These functions are designed to execute critical tasks without interruptions caused by the JIT checkpointing, ensuring reliability and consistency. I will elaborate on various aspects of SAMR atomic functions further. First is the syntax. Atomic functions are defined using specific syntax to indicate their atomic nature and provide necessary parameters. The syntax includes a knob value, a knob, and a value. Atomic keyword is used to declare a function as atomic, which allows the programmer to specify knob variables and their initial values. Then it also includes some qualifiers like input, output, and inout. Qualifiers for function parameters indicating indicate whether they are used for input or output or for both. The scaling rule. Optional scaling rule is an optional rule specifying how to recursively decompose the function if it consumes too much energy. And the last is fallback. Fallback is an optional routine to execute if the recursive decomposition fails to produce a terminating execution. Now we'll discuss how to write an atomic function using the syntax discussed. Writing an atomic function involves several steps. First is annotating the function as atomic and then specifying the knob variables and their initial values. Second is defining the parameters as input, output, or both using the appropriate qualifiers. Then we proceed on implementing the peripheral control code within the function. Furthermore, optionally, defining a scaling rule to recursively decompose a function if it consumes excessive energy and providing a fallback routine to execute if the recursive decomposition fails. Now, how does SAMR execute these atomic functions? What it basically does is, upon entering an atomic function, SAMR disables the automatic just-in-time checkpoints and collects a checkpoint to ensure restartability. It then decides whether to execute the main workload or apply the scaling rule based on the prior execution history, the knob values, and the progress indicators. If executing the main workload, Samoid ensures it completes successfully or initiates a scaling down of the workload if needed. If the workload fails to complete after multiple attempts, Samoid updates the knob values and/or applies the scaling rule accordingly. Samoid's execution strategy prioritizes safe and efficient operation while adapting to energy constraints dynamically. Now, Samoid ensures memory consistency and termination guarantees for atomic functions. It, it also prevents the memory inconsistencies by carefully managing the undo log and ensuring proper initialization of the variables. By utilizing the scaling rules and fallback mechanisms, Samoid also avoids non-termination scenarios, ensuring that functions can complete within the specified constraints. And this is how the correctness of the working of Samoid is verified. Since Samoid supports sophisticated scaling rules and multi-knob configurations, which allows the programmers to define complex atomic functions tailored to specific requirements. It offers flexibility in defining scaling rules, which can be recursive decompositions or calls to lower energy peripheral routines. This generality enables Samoy to adapt to diverse application scenarios and hardware configurations effectively. The next crucial component of SAMOID is the energy profiler. It serves as a crucial tool for assessing the viability of the atomic functions just discussed on a given platform by directly measuring the energy consumption of each function. To further elaborate, the primary objective of this energy profiler is to estimate whether an atomic function can execute within the energy constraints of a specific platform. It provides valuable insights into whether a function's energy demand exceeds the device's energy supply, aiding to programmers in making informed decisions about function deployment. The compiler generates a measurement binary that includes the original device's initialization code along with the atomic function. This binary is programmed onto the target platform for energy measurement. The energy measurement hardware repeatedly fills the device's energy capacitor, detaches the power source, and signals the device to run the measurement binary. The device executes the atomic function until the energy is depleted, and the resulting number of successful executions is sent back to the measurement hardware. For statistical analysis, the aggregated statistics from multiple runs provide insights into the function's energy consumption behavior on the platform. Programmers can analyze these statistics to determine the function's feasibility and identify potential energy bottlenecks. Now, some of the use cases of these include platform evaluation, energy budgeting, and deployment decision making. Now, the energy profiler helps evaluate the suitability of a platform for executing specific atomic functions. If the platform cannot run the function even once with a fully charged capacitor, programmers may need to consider alternative platforms or adjust the energy parameters. By understanding the energy consumption patterns of atomic functions, programmers can allocate energy resources more effectively, They can identify the functions that consume excessive energy and optimize or prioritize them accordingly. The profiler also assists programmers in deciding whether to deploy a function on a particular platform based on its energy requirements. If a function consistently exceeds the platform's energy budget, then the programmers may need to reconsider its deployment or modify the function to reduce the energy consumption. After this, the energy profiler still has some limitations. The energy consumption may vary depending on factors such as the input data, dynamic hardware configurations, and environmental conditions. The profiler provides estimates based on measured data but cannot guarantee any precise energy consumption under all conditions. The profiler assumes certain conditions such as fully charged capacitors and consistent energy delivery, which may not always hold true in the real world scenarios. Programmers should interpret the profiler results with awareness of these assumptions. This profiler offers empirical evidence of a function's energy consumption behavior, providing the programmer with additional confidence in function viability. It Programmers can also use it to profile results as a basis for decision making regarding function deployment, platform selection, and energy budgeting, contributing to more informed and efficient development processes. Overall, the energy profiler in SAMOID plays a critical role in assessing and optimizing energy utilization in intermittent systems, facilitating the development of reliable and energy efficient applications. Now, looking at the key contributions, SAMUD achieves secure execution of user-annotated peripheral functions by strategically disabling the checkpoints and undo logging the mechanisms. This tactic ensures that vital peripheral operations can proceed without interruptions caused by checkpointing, thereby preserving the integrity and consistency of these functions. By permitting the uninterrupted execution, SAMUD ensures steady progress in task completion and prevents potential failures stemming from checkpoint-related inconsistencies. Additionally, SAMUD harnesses accelerators to realize notable speed enhancements in computationally intensive tasks. Through efficient utilization of hardware accelerators, SAMUD boosts the performance, reduces the execution times, and enhances the overall system efficiency. In contrast to the existing systems and alternative methodologies, SAMOID exhibits significant performance advantages. It surpasses the prior JIT checkpointing system by facilitating accelerator utilization, resulting in speed gains of up to 122.9 times in select benchmarks. Furthermore, SAMUD's dynamic workload scaling and energy profiling capabilities enhance its efficiency in handling the peripheral operations, leading to improved performance and energy usage. The system's adaptability to varying energy constraints and its ability to optimize the task execution based on available resources distinguish it from the conventional approaches, underscoring its efficacy in supporting peripherals in intermittent systems and highlighting its superiority in achieving substantial performance improvements. In the, in the implementation of SAMOID, the authors have focused on tailoring the hardware, runtime library, compiler, and energy profiler to the specific requirements of the Capybara platform. They optimize the SAMOID hardware to align with the capabilities of the Capybara system, which featured a TI MSP430FR 5994 microcontroller along with various peripherals such as an AES accelerator, a LIA DSP accelerator, a Bluetooth radio controller, and sensors linked via I2C. To monitor the energy buffering capacitor reliably, they utilize the microcontroller's internal comparator, triggering an interrupt at 1.8 volt, ensuring dependable checkpointing. They also aim to minimize the energy overhead, considering that the comparator's energy consumption ranged from 1% to 7% of the microcontroller's total energy usage. The team meticulously crafted the Samoid runtime library to manage checkpointing, undo logging, restoration, and dynamic scaling. Critical data, including the checkpointed register contents and undo logs, were allocated within a designated FRAM buffer. Leveraging DMA, they streamlined the process of undo logging multiple elements in arrays. Upon reboot, the system seamlessly restored register data, program counter states, and any undo logged information, ensuring continuity of the operation. The restoration routine also addressed specific flags such as NP and need update, crucial for system stability under varying conditions, particularly the power failures. Given that MSP430FR5994 microcontroller boasted both the SRAM and the FRAM as primary memory, the team devised a custom linker script directing the microcontroller to exclusively utilize the FRAM during program execution. This optimization strategy aimed to enhance efficiency and streamline the memory utilization. The team also developed the Samoid compiler as a source-to-source transformation tool, leveraging the libtooling, a CLang-based front-end. This approach allowed for the detailed analysis of the abstract syntax tree and facilitated the generation of instrumented C code. By employing GCC for compilation, they ensured compatibility and efficiency, circumventing potential inefficiencies associated with the experimental MSP430 LLVM backend. For energy profiling, the team has utilized an additional MSP430FR 5994 microcontroller interfacing with a SIP32431 load switch to measure the energy consumption. Data collection was facilitated through UART communication, providing valuable insights into energy utilization patterns for informed decision making. The evaluation results for Samoid showcase its proficiency in successfully executing peripheral operations that pose challenges for existing systems, highlighting its reliability and effectiveness in managing critical tasks. The system achieves significant speedups with performance gains of up to 122.9 times in certain benchmarks, showcasing its efficiency in optimizing task execution. These speedups not only enhance the system performance but also simplify programming in intermittent systems by streamlining the process of managing peripherals and adapting to varying energy constraints. Samoyed's ability to dynamically scale these workloads, profile the energy consumption, and provide fallback mechanism contributes to a more straightforward and efficient programming experience in intermittent computing environments. In conclusion, the key takeaways from the paper on Samoyed include its ability to safely and efficiently manage the peripheral operations in intermittent systems through selective checkpointing and dynamic workload scaling. The system demonstrates significant speedups up to 122.9 times in benchmarks, showcasing its performance benefits and impact on simplifying programming in such environments. Future research directions for SAMOID could include further optimization for specific types of peripherals, enhancing energy profiling accuracy, and exploring the applications in diverse fields such as IoT devices, sensor networks, and edge computing. The system's adaptability and efficiency make it a promising tool for addressing challenges in intermittent computing and advancing the development of reliable and high performance systems in the future. Thank you.